Okay, this is hazard analysis number 13. It's record number 14. We've highlighted it. We're going to load it into the interface by going up to the add-ins. This will give us the Easy As PDB menu, load parameters from PDB record, and we have the parameters loaded. Now what this laser system really is, it's two lasers, frequency doubled YAGs, running short pulse durations, and they're used as a strobe for a camera to measure particle velocity. So what happens, you really have two laser heads. We set the timing on the laser heads to give us a temporal spacing that we're looking for, and typically this is going to be from 100 nanoseconds to no more than 2 microseconds. Okay, so that we take two pictures. From the two pictures we have a distance that the particle traveled, and we have the time that it took the particle to travel that distance, so we can calculate the velocity. Now what's special about this particular analysis is you'll notice that we have combined the energies of the pulse. Let me explain why. Let's go look at the standard and go to table 1, and we're going to find something in here called T-min. For our wavelength of 532, T-min is 5 microseconds. What this means is that any number of pulses that happen within 5 microseconds, we sum their energies and treat it as one pulse. All right? So since both of the pulses from our particle measuring lasers are going to be fired within 5 microseconds, we add the energies and treat them as a single pulse. Now you'll notice that we're using the time duration of a single pulse out of one of these lasers. Let me show you why we can do that. Let me get to the correct page. Here's our table. Oops, one more down. Here's our table. Here is for our 532 wavelength. Here's T-min of 5 microseconds. And we'll notice that from 10 picoseconds to 5 microseconds, the MPE is constant. It's 2 times 10 to the minus 7th joules per square centimeter. So whether we used the time duration between two pulses, in other words, if we fire both of these pulses and they're separated, let's say, by 500 nanoseconds, whether we use 500 nanoseconds or we use 8 nanoseconds, the MPE is the same. That's the reason we can combine the energies and just use the pulse duration of the single pulse. Okay, so now let's get back to our hazard analysis. The other thing we want to point out is that with one of these systems you have to create a fan or a plane of light. We do this by using a rectangular top hat, and we model the beam that is optically produced from one of these systems by saying, well, we're going to create a plane, so our major axis will be just a 1 millimeter in diameter, and then our minor axis is going to be a 0.5 millimeter in diameter, but with a really large divergence. So we keep one axis narrow. Okay, that's going to give us our fan. That's going to give us the narrow part of our fan, and then we keep the other axis, we have it narrow, but with a really big divergence. Okay, so that creates the fan for this. Now we can tell that at an observer range of a 0.5 meter, the major diameter is only 1.06 millimeters, but our minor diameter, our beam diameter, or the width of our fan is almost 175 millimeters. So this is how we model a fan for one of these type of systems that measures particle velocity. You'll notice the worst case OD is 6.7. Yeah, these are significantly hazardous lasers. OD at observer range, though, of course, is only 5.3, and that's because the beam is so large with a 7 millimeter aperture, we're only passing 4% of the power through the limiting aperture. Okay? So really, we want to discuss with this a little bit about how to create a fan, how to model a fan beam, or a beam that what we would call a line generator, and also how T-min plays into this and why we would simply sum the energies of the two pulses and yet use the pulse duration of only one pulse. Okay, that's about it. Oh, one more thing. I believe the slide did ask what happens if you only got a 4% reflection from this. Well, a 4% reflection would be 0.016 joules. Okay, and we can still see you have a significant hazard even from a 4% reflection from this thing. Okay, all right, so now I'm sure this is it for this one.